for the last talk in our session, we have a familiar face. Dimitris will speak to us again.
All right, thank you. All right, I'm Dimitris. I'm a cryptography researcher at Nilion, and this work is a joint work with Daniel Masni, Nitrio, Subos Gupta, Prasad Budhavarapu, and Benjamin Case. This work is called Delegated Private Matching for Compute. And to introduce you to the problem of the private matching for compute before we talk about delegation, there exists previous work that tries to do unions, private unions. Essentially, we have two parties, party C on the left-hand side and party P on the right-hand side. And here, we want to create a union in a sense that each of the two parties will not be able to learn which of the records have matched on the other party, and they don't learn anything apart from some intersection sizes. This is very useful because we can do many applications with that, starting from add attribution, where on one party you might have add impressions, like what clicks you have done, and so on. And on the other party, we might have add conversions. And joining these enables us to see how ads are performing, and later on we can do personalization in a privacy-preserving way, and so on and so forth. So in this setting of private ID, we can assume that both parties, as they run the matching protocol, they are online, and then they continue being online in order to do the downstream computation that I just mentioned. In that setting, both parties can bring some associated data. For simplicity here, let's assume some dollar amounts. And what can happen is that they can secret share this data and run the computation, which is easy to do when we just care about two parties. But when we have multiple parties, this becomes problematic. One of the reasons is that the first phase is the MVC phase to compute the matching. And it's easy to assume that not many parties are interested in doing this computation, this heavyweight computation of computing the private matching. And also, after you do the matching, then you also have to do another MPC computation to do the application. So this is not easily scalable. As a result, we propose the delegated private ID, and we replace the party on the right-hand side with a delegate server. And the idea here is multiple parties can offload their computation, can offload their data over an encrypted form. And then these parties also have the associated data. And at the end of the protocol, the ideal functionality that we have is that both party C and the delegate party can end up with secret shares of the associated data for the rows that have matched. So if an identifier exists in party 1, let's say, and also in party C, then both parties D and C will end up with secret shares of the associated values for the row that has matched. And for every other row, we will end up with secret shares of 0. We quickly realized that although previous works have focused on joins and on unions and intersections, we actually can do something different here, and we focused on left join. The reason that we focus on left join is that when we have two parties, we have this associated data that both parties can bring in the computation. The associated data can be the dollar amounts that I mentioned, some timestamps, and so on. And again, this highly depends on the application. But now that we're on the delegated setting, and all the parties P send their data and then they can go offline, then there's actually no reason of keeping the rows that are not present in parties C dataset. So just by focusing on the left join instead of the union, we can essentially speed things up. In the paper, we studied two protocols. Both of them have party C and party D, the delegate server. And the second one also has an additional party, which we call a shuffler. And then the input parties are multiple parties P, which offload their data. In the interest of time, I'll focus on the first one. The second one is also in the paper. So I'm abstracting out a lot of details here. I hope you get the general idea. And on the right-hand side, because many parties will not fit the slide, I just assume one party, but having multiple parties is the same, essentially. So Party C has a database of 4 items, and Party P has a database of 3 items, and Party P also has these associated values, the dollar amounts. First, what both parties do is that they use some secret local key to encrypt their identifiers, and then the Party P uses a key encapsulation mechanism to essentially create some symmetric keys and some ciphertext, and uses the keys to blind the associated data. With that, Party P also uses this public key and encrypts the associated data, sends everything to Party C, and then Party P can go offline. From here, Party C applies the red encryption over the green encryption and sends everything to Party D. Now Party D has everything they need to do in order to continue the computation. They have their blue key, so they can remove the blue layer of encryption. Now Party D acquires the green key and can remove the green layer of encryption from the identifiers. And Party D can now perform the matching between the different identifiers. One problem here is that since Party D performs the matching, they actually learn the intersection sizes between Party C and each of the databases of Parties P. So for each row that has matched, for instance, Alice here, what Party D will do is that it will send over the ciphertext, which they acquired from the key encapsulation mechanism, and Party C will decrypt this and acquire the same key. This is the definition of a key, essentially. For the rows that have not matched, Party D will just create a new encapsulation, keep the local key, send over the ciphertext, and by decrypting, Party C will acquire the same key. So essentially, effectively now that both parties have ended up with secret shares of 0 for the rows that have not matched, and secret shares of the associated data, the initial associated data, for the rows that matched. So this has a problem, and what I mentioned before, that since Party D performs the matching, if we have multiple Parties P, D will learn multiple intersection sizes. In some cases, that's okay. In some cases, that might be very problematic. So to solve this problem, we have the second protocol, which I will skip from this presentation. But the high-level idea is that we have a new OPRF that allows multiple senders to send their data. And then we can re-randomize the ciphertext and also shuffle them. And we use this property to essentially mix data from multiple Parties P and hide all these intersection sizes when the delegate node performs the intersection, or the left join. Moving to experiments, the simplest scenario, we have one Party P, and this does not do justice in our work because we focus on the multiple Parties P on the right-hand side. But with one party, and this is with increasing database sizes, you can see that our works are somewhere in the middle. Below the blue and the orange, which are the two protocols that we have created, is the private matching for compute, which is a very similar work, but without the associated data. So this work essentially assumes that both parties are online. Since they are online, like the associated data can offload it later on. However, in our protocol, all our communication has to carry this associated data. So this extra overhead comes mostly from communication. And then fastest is the circuit PSI, which is actually really good. However, again, this is only focused on two nodes. When we go to see the runtime of each Party P, and here's like where our work is interesting, is when the data set of the Parties P is small, then the party is only doing linear work to their data set size, and then they send their data and they go offline, which is not the case for other protocols that require both parties to be online all the time. To wrap up, we have delegated protocols, two new delegated protocols that allows multiple parties to offload their data and perform the matching, and then the delegate server and also the Party C can run different applications, different MPC applications based on the secret shared associated values. These applications could include ad attribution, personalization, and so on, any other computation that you can do over secret shared data, essentially. And we solve the problem of the intersection sizes with a new OPRF primitive that does shuffling and randomization. Thank you.
Okay, we have time for a question or two.
Yeah, so thanks for the presentation. So if I understand correctly, so you have this, in your process, you have these two layers of encryption, and you assume that you're able to remove the inner layer without touching the outer ones, right? So you do set this condition on your
Yeah, that's correct.
encryption.
So it's some type of homomorphism that goes on there.
Okay, so you require some homomorphic property.
Yeah, essentially it's exponentiation, has an exponentiation. So when you exponentiate both, like you can remove one of the two exponents, so you end up with the other. But you can instantiate it with different schemes as well. In the paper, we try to abstract it out as much as, and for the CAM as well, we have a very similar property. But for the CAM, how we instantiate it versus how we present the protocol, you can do different things there.
Okay, thanks.
Thanks.
Thank you for the nice presentation. My question is a more general one. How does it scale with the increasing number of parties?
So we have some graphs on the paper. I just picked two out of them. The good thing, when I go here, for instance, this is just one party, and both parties have the same database size. So now if instead of one party have 10 parties, parties P, each of the parties P essentially does 1/10 of the work, whereas the total execution time remains the same.
Oh.
So it's kind of heavy for party C, but for party C, like the smaller database you have, like the better it is.
Okay. Thank you.
Okay, let's thank all our speakers again.